Alright, this video is over polynomial functions of higher degree. Polynomial functions of higher degree. Okay, when we take a look at graphs of functions, there's a couple or a lot of important things to talk about. So first off, hopefully we're going to get through all those things in this video, but I want to first talk about two really important aspects that are particular to any polynomial. The first is that all polynomials are continuous, which means that they don't have any stopping points. So a polynomial could go like this, it just makes a couple turns, and then it continues forever. There's no stopping points. There's no point where the polynomial goes, whoop, I'm going to stop, and then I'm going to take a break again, and then continue on over here. There's no breaks in the graph like that whatsoever. It is a continuous graph from negative infinity to positive infinity. The other important aspect is that there's no sharp turns. Okay, no sharp turns. All the turns are smooth and continuous. So it's not like it goes like this, right, where it makes a sharp turn. That is like an absolute value equation, then which is not what we're talking about. So none of those. We're talking about all nice, smooth turns. That's another important aspect of all polynomial functions. Okay, now that we got the two major things covered, we're going to talk about a bunch of small things now. First off, the even power or an odd power. We're talking about the degree, right? We're talking about the degree. What's the degree? Is it an even degree or is it an odd degree? First, if it's even degree, then we know a whole lot of stuff because of that alone. Even degrees, the ends do the same thing. So either both ends go up or both ends go down. They do the same, both up or both down. Now, what happens in between? Well, it could make several different turns, but it always ends up coming back up. Or if the left end is down, it might make a whole bunch of turns, but the other end is also down. So even degrees, like 2, 4, 6, 8, always do the same thing. Odd powers, one end is up, one end is down. So if the left side is up, then maybe it does a couple turns, and then the right side is down. Or if the left side is down, then it might make a couple turns, but the right side is up. So we have even, they both do the same thing, whether it's up or down. Odd, one end is up, one end is down. Now, we have what's called the leading coefficient. Now, the leading coefficient, you got to be careful. It sounds like it's the very first coefficient, but it's the coefficient that's attached to the highest power, right? So it's the coefficient that is next to the largest exponent, which not necessarily has to go first. It typically should go first, but you got to make sure you're looking at the right leading coefficient. We're going to call that A. Now, if you are an even degree, and you have a leading coefficient that's positive, greater than 0 means positive, then both ends will be going up. Now, what happens in the middle? Not quite sure, but both ends are going up. So if you have an even degree, that tells you they're both doing the same thing. The fact that leading coefficient is positive, it tells you they're both going up. If your leading coefficient is negative, and you're an even degree, then both ends are going down. So once again, we're not quite sure what happens in between. Maybe there's a whole bunch of turns in between, but the other end is going down. So that's even with a negative leading coefficient. Okay, odd with a positive coefficient. Odd with a positive coefficient. This is where your left side is going down, and who knows what's happening in between, but the right side is going up. This is with a positive leading coefficient with an odd degree. If you have an odd degree with a negative leading coefficient, then your left side is up. Who knows what's going on between, but the right side is down. So you got to make sure you understand how the leading coefficient, being positive or negative, affects the graph, as well does the degree. Okay, now, describing end behavior. End behaviors, we're talking about what's happening on the ends of the graph. So here we want to know what the function values are doing as x goes to the right, which is infinity, or as x goes to the left, which is negative infinity. So let me just draw you a picture. Here is a picture of an even degree with a positive exponent. Okay, or I'm sorry, positive leading coefficient. So here is it going to be, left side is going to be up, going to make a couple turns in between, and then the right side is also up. So here, I might say to you, what is the end behavior? What's happening as x is going towards infinity? Now notice my symbol here, I'm just using an arrow. So as x goes towards infinity, where is the function going? Well, the function is the graph itself. Function values are also known as the y values. So as x goes to the right, my function values are going up towards infinity. And as x goes towards negative infinity, my function values are going towards infinity as well. So notice as I go to the left, on the x, my function is going up. So my function values are going towards infinity, and same thing with the right. So as I move to the right, my function values are also going up. So this is the notation that we use. We use these little arrows, and we use the infinities to understand what's going on with the end behavior. All right, let's talk about a odd degree that is negative leading coefficients. That means the left side is up, and a couple turns in here, right side is down. So again, we say as x goes towards infinity, where is the function going? Well, as x goes towards infinity, the function is going down towards negative infinity. And then we might say, what happens as x goes towards negative infinity? That means we're talking about going to the left, and the function is going up towards positive infinity. Okay, so note that when you're even, they're both functions, both ends are doing the same thing. When you're odd, one's going up, one's going down, and it all depends upon that leading coefficient. So we call that end behavior. So make sure you understand that. Now, another important aspect of any graph, we got done talking about the ends, right? Going up, going down, and so forth, even, odd. Now we're going to talk about the zeros. We notice that we somehow incorporate zeros in pretty much every lesson in this class. So the zeros are a really important part of any polynomial. Now, if w is found to be a zero, this tells us four things. If w is a zero, it tells us that x equals w is a zero. X equals w is a solution, just another word for a zero. It tells us that x minus w is a factor, and it also tells us that w comma 0 is the x-intercept. So if I said, hey, x equals 5 is a 0, then that means that x equals 5 is a 0. It means that x equals 5 is a solution. It means that x minus 5 is a factor. And it means that 5 comma 0 is the x-intercept on the graph. So knowing that we have a 0 tells us an awful lot. Let's do one more. If x equals radical 3 is a 0, then that means x equals radical 3 is a solution. That means that x minus radical 3 is a factor, and that means that radical 3 comma 0 is an x-intercept of the graph. Now, we did learn that if you know a square root is, the square roots always come in pairs, so that means if the square root of 3 is a 0, then you automatically know negative square root of 3 is another 0. We learned that already. All right, now, the degree of a polynomial is actually really, really important. It tells us two really important things. First, it tells us that the function will have at most n zeros, meaning that whatever your degree is, if our degree is n, I'm just using a generic n, that's how many zeros you could have at most. So if we have a polynomial like this one, 3x to the 5th minus 6x squared plus 2. Okay, now my degree is the 5 right here, the largest exponent. That means that I have at most 5 real zeros. So I can have 5 zeros, 4 zeros, 3 zeros, 2 zeros, or 1 zero. Now, could I have 0 zeros? Well, no, and this is because it's odd. Since I'm odd, I know that one side is going up and one side is going down. What happens in between, I don't know. But think about it. If one side's going up and one side's going down, there must be at least 1 0. There has to be. So if you have an odd degree, the fact that the left and the right ends are doing something different, you absolutely have to have at least 1 0. Now, if you have an even degree, remember both ends are going up, and if that is all above the x-axis, you could end up with no zeros. So keep that in mind as well. So the degree tells you at most how many zeros you could have. So 5, 4, 3, 2, 1. You could also have 0 or no zeros, but you got to be careful with an odd function. or with an odd degree, you got to have at least one. All right, now, also the degree tells us that the function will have at most n minus 1 turning points. So that's you're taking your degree and subtracting 1. So let's go back to this function right here where my degree was 5. 5 minus 1 is 4. So I could have at most 4 turning points. I could have 4, I could have 3, could have 2. Could I only have 1 turning point with this type of function? No, because I'm odd. Remember, an odd function has to have at least 1 turning point. The fact that it was going down and now it's going up. So it had to turn around at some point, right? Whereas an even function that both going in the same direction would have 1 turning point. So now if I have a function that is this one. Let's just talk about this function right up here. Now, I know that I have at most 4 turning points. So I know my left side is going down because my leading coefficient is positive. So there's 1 turning point. There's 2 turning points. There's 3 turning points. That right there could be my function with 1, 2, 3, 4 turning points. That could be my function. I can't have 5 turning points or more, right? Why can't I have 5 turning points? Watch this. 1 turning point, 2 turning points, 3 turning points, 4 turning points, 5 turning points, and now I'm going down. 1, 2, 3, 4, 5. How come this can't work? Oh, because both ends are going down. That would have to be an even function. This is obviously an odd function. So the degree tells us at most how many zeros we could have, and n minus 1, your degree minus 1, tells us at most how many turning points you could have. All right, now we also have something that comes up in a lot of polynomials called repeated zeros. Now, repeated zeros are zeros that come up twice. Let me give you an example here. For example, the function x plus 2 times x plus 2 times x minus 1. Notice that this has zeros of negative 2, negative 2, and positive 1. Well, negative 2 is what we call repeated zero. I also could write that as x plus 2 squared times x minus 1. So that negative 2 is a zero that's repeated. We say that that zero has a multiplicity of 2. Here's another one right here, x plus 5 cubed. Obviously, I could write x plus 5 times x plus 5 times x plus 5 times x minus 3. But this would have a multiplicity of 3. So I have 2 zeros, negative 5 and positive 3, but the negative 5 got repeated 3 times. So what does this tell us? Well, if x minus w is a repeated zero and it's repeated k times, so w is my 0 and k is how many times it's repeated. If it's repeated an odd number of times, like 1, 3, 5, 7, then that 0 is a crossing point, meaning at that value the graph crosses w. It crosses at that value. So if here's my function and here's w right here, then that means here comes my graph and I cross at that point to make a 0. Okay? Now, if my multiplicity is even means 2, 4, 6, 8, so forth, then I don't cross at that point, I just touch. So a touch would look like this. So let's just say here's w right there, and let's say at a multiplicity of 2, I don't cross, I just touch and come back down. Okay? That would be an even multiplicity. So in this example right here, where negative 2 is repeated twice, since repeated twice is an even amount, then at negative 2, I don't cross, I just touch. So, in this particular graph, here's negative 2, and here is positive 1. Again, not really great to scale, but you get the idea of my 2 pictures. So I must look something like this, where I I touch here, and then I do something else, and then I come back and cross it once. See, 1 was just 1 time, right? That's odd. 1 is odd, so I cross at 1, and 2 is even, so I must touch at negative 2. Okay, so hopefully you get an idea of what that function looks like based on repeated zeros. All right, so now I want to take everything we learned and kind of put it together and look at a couple of examples. So the first example is negative 2x to the fourth plus 2x squared. So what do we know? First off, we know that we have an even degree of 4. That means we have at most 4 zeros. Okay, I could have 4, 3, 2, 1, or because I'm even, I could even have no zeros. I have at most 3 turning points. So I could turn around 3 times, 2 times, or 1 time. We'll talk about that in a moment. Let's see here. I know my end behavior, right? Because I'm negative leading coefficient with an even degree, that means that both ends are going down. Now, I don't know quite what's going on in the middle, but I know that both ends are going down. So I know a lot just from looking at the function itself. Next, obviously, we did that whole lesson on zeros. Zeros are pretty important, so let's talk about the zeros real quick. To find the zeros of this function, I'm going to turn the function into 0. And I'm going to factor this guy. So I'm going to pull out a negative 2x squared. So that's going to leave me with x squared minus 1. Let me just check and see if this is right. So negative 2x squared times x squared is negative 2x to the fourth. Negative 2x squared times negative 1 would be positive 2x squared. So I can continue to factor this because that is going to be x minus 1 times x plus 1. Okay, let's talk about my zeros. My zeros are very obvious one I see here at 1, and another obvious one I see here at negative 1. Those are multiplicity of 1. They only occur one time, so those are going to be crossing points. Now, here's another 0 at 0. Right? Because of the negative 2x squared, if I set negative 2x squared equal to 0 and solve, I get x equals 0 as another 0. But because that had an even multiplicity, that means I'm going to touch here. So I'm going to touch at 0, I'm going to cross at 1, and I'm going to cross at negative 1. So hopefully you could take everything we've learned in this video so far and apply it to this problem. I think that's kind of cool. So if we were to think about what this graph looks like, okay, I'm going to make a quick picture of this graph. It might not be 100% accurate, but it should be pretty good. All right, let's see here. I cross at 0. I'm sorry, touch at 0. Here's negative 1. I know that I crossed there. Here's positive 1. I know that I crossed there. And I know both ends are down. So my graph probably does something like this, where it's going down, it was down, then it comes up here and it crosses, and then it's got to come down here and just touch, and then it comes back up, and then it's got to go back down at 1 and cross. So there it crosses at negative 1 and positive 1. It touches at 0, and there is 1, 2, 3 turning points, which was a possibility. Could have at most 3 turning points, and I only have 3 zeros. Remember, I could have at most 4 zeros, but at most means 4 or less, so I only had 3 zeros with this one. So there is a very rough picture of what is happening with this function, and I think that's pretty cool. I think we learned a lot just by looking. Didn't even need a calculator to understand any of that. Okay, here's another one. Let's talk about this one right here. 3x to the fourth minus 4x cubed. All right, let's first talk about the fact that this is another even degree. So that means that it's going to, and then, with a positive exponent, or leading coefficient, sorry, positive leading coefficient. So that means that both ends are going to go up. Something's going to happen in between, but both ends are going to go up. Let's see here. I have at most 4 zeros. Because of my degree, I have at most 3 turning points. Okay, and let's talk about end behavior. As x goes to the left, as x goes towards negative infinity, my function is going towards positive infinity, and that's because I know this. As I go left, my function goes up. As I go right, my function also goes up. So as x goes towards infinity, my function goes towards, not an equal sign, an arrow, towards positive infinity as well. Okay, let's talk about zeros. Zeros is always an important part here. So I'm going to factor out an x cubed. So that leaves me with a 3x minus 4. Double check, 3x, or x cubed times 3x is 3x to the fourth. X cubed times negative 4 is negative 4x cubed. Okay, so let's see here. Looks like I'm going to get a 0 of 4/3. That's pretty easy for everyone to see. 4/3 is approximately 1.3 repeating. X cubed, okay, that is a 0 of 0, but it is a cross because it has a triple multiplicity, a multiplicity of 3. What about the 4/3? It had a multiplicity of 1. The power right here is 1. So I also cross at 4/3. I do not touch at 4/3. I cross. So let's draw a quick picture of this graph. Okay, let's see here. I'm going to go ahead and put on some values here. 1, 2, 3, negative 1. Okay, there we go. 1, 2, 3, 4, 5. Okay, so at 0, I definitely cross. At 4/3, which is about 1.3, right there approximately, also cross. I know both ends go up. So I must be up here somewhere. I come and cross. I come and cross again, and I go back up. Now, again, that's really not the nicest picture that I've ever seen before, but I know that it's got to be something like that. Now, here there's only one turning point. There could be a couple more turning points. I'll give you another example of what this picture could look like. It could come down here, cross. It could make a couple turns in there, and then come back up as long as it crosses at 4/3 and 0, and both ends go up. And I know that that's really a poor picture. But again, we're just focusing on the things that we know just from looking at the function. All right, let's take a look at another one here. Not too much longer. All right, what do we know? Well, we know that we have an odd degree, and we know that we have a negative leading coefficient. Okay, so that means that the left side is up. Who knows about the middle? And the right side is down. Odd tells me that one's up, one's down. The negative leading coefficient tells me the left side's up, right side's down. Okay, so that is taken care of, which is pretty nice. Let's see here. I know that there are at most 3 zeros. And I know that there are at most 2 turning points. Okay, and let's talk about zeros real quick. Well, let's see here. What could I factor out of this? This is pretty ugly. Let's see here. I don't like fractions. Watch what I'm going to do here. I don't like negatives either. I'm going to factor out a negative 1/2 x. Now, it's pretty obvious why I'm factoring out the x. Why am I factoring out a negative 1/2? Well, I'm factoring out a negative because I don't like a negative in front here. So that's why I'm doing that. And I'm factoring out a half because a half is what my denominator is, and that's going to help me get rid of that. So watch what happens here. So here I'm going to get 4x squared plus 12x plus 9. Now let me explain. Negative 1/2 times 4 does make the negative 2 and the x cubed. Negative 1/2 times 12 does make the, I should have had a negative 12 there. I apologize. A little mistake there by me. That should have been a negative 12. That way a negative times a negative makes the positive 6. And the negative 1/2 times 9 makes the negative 9/2. So now, because I pulled out the fraction, I get all nice numbers over here. And that's important because this guy could actually be factored more. This could be factored to 2x plus 3 times 2x minus 3. Again, 2x times 2x is 4x squared. 3 times negative 3. Another blunder there. Sorry, I'm making all kinds of mistakes. Should be a negative 3 because I need a negative 3 times a negative 3 to make the positive 9. And then I have a negative 6x on the outside and negative 6 on the inside to make that negative 12x there in the middle. So essentially I get negative 1/2 x, and then I get 2x minus 3 squared because that is a repeated 0. 2x minus 3 is the same thing as 2x minus 3. Now, how did I recognize that, by the way? Because 4 is a perfect number and 9 is a perfect number. If both of those are perfect numbers, you might want to start thinking about factoring for sure. All right, so that means I have zeros of 3/2. And that's going to be a touch because it has an even multiplicity. It was repeated twice. This negative 1/2 x right here is going to make a 0 at 0, and that's going to be a cross because it has a multiplicity of 1. So if I were to make a quick picture of this, let's see here. Let's give a couple little lines here just so I can have something to base it on. Let's see here. Okay, at 0, I know that I'm going to cross. And at 1.5 or 3/2 right here, I also know I'm going to touch. Now I know that the left side is up, so I must be going up like that. I must come down here, and then I must turn around, and then I touch, remember, at 3/2, and then I come back down. So now I was able to follow all of my rules of this being an odd function. There is 2 turning points, which is completely legit. I was allowed to have at most 2 turning points. My end behaviors are correct. I got my crossing 0. I got my touching 0. Everything is just perfect and beautiful there. So very, very nice job. All right, so the last thing I want to talk about is something that we call the intermediate value theorem. I'll explain a lot more in class, but I want to write down here. I want you to make sure you have in your notes what this is. So first off, we say let A and B, A and B be real numbers. So they're not irrational, they're not imaginary, they're real numbers, such that A is less than B if f of x is a polynomial function such that f of a does not equal f of b, which means that a and b got to be different, then the interval from a to b, with brackets, meaning including a and including b, f of x takes on every value between f of a and f of b. Now, you might be like, what? Take a moment, pause if you have to write that down. Let a and b be real numbers, such that a is less than b. If f of x is a polynomial function such that f of a does not equal f of b, then the interval a to b, or then in the interval from a to b, f of x takes on every value between f of a and f of b. Now let me explain this with a very simple picture. This is kind of like a theorem, but it is really important mathematically. So if we have a and b, and a is less than b, which means a comes first and then b, a and b cannot be the same, and f of x, or f of a and f of b is not the same, which means that a must map me somewhere over to here to f of a. So here's a point right here, f of a, comma f of a, and then here's another point over here where I got f of b. So a took me to f of a, b took me to f of b. In between, in this interval, so from a to b, in that interval, I take on every value. All that means is I'm continuous. What's happening in there, I don't really know. There could be some turns. I just know that I'm continuous. I could have no turns, and I'm just a nice smooth curve going straight there. I could have several turns. I can go up, and then I can go down, and I can come back up. But the whole point is that in that interval, I'm continuous. Now, this may seem like a dumb theorem, but it's really, really important to understand that if you have a polynomial function between two values, a and b, you are continuous, which means that the function takes on every value from a to b. There's no gaps, there's no jumps, there's no skips. The function's continuous from a to b. That's what the intermediate value theorem tells us. We'll talk more about that in class. All right, hope you enjoyed the video. Hope it was all very, very simple. I think it was, and I will see you in class.